Hey everyone, this is a video lesson that I'm using as a supplement in my AP Calculus AB class. I'm putting this online in case it would be helpful to others as well. This is the third video for the current section that we were working on that is all about the definition of a derivative. So far in video 1, we talked about the original definition of a derivative, that is the limit formula as h approaches 0. In video 2, we talked about the alternate definition of derivative, that is the limit formula as x approaches a. There is a link to a printable set of notes that you can follow along with the examples that I go over. It is in the description of video 1 for this section, so you can find it there. I'm really excited about this third video today because I've been mentioning for quite some time now that there are little derivative rules and formulas and what you might call shortcuts to finding derivative values, and we're going to start to uncover some of them today. So that's pretty exciting. I think it's exciting because it really gets at the essence of what a derivative is. You know, so far we've been finding like derivative values at one point on a curve, or we can call that the slope of a tangent line. But really the derivative, like the essence of a derivative, is taking a function or, something that is not a constant rate of change and defining the rate of change for that curve as a function itself, which is, really exciting. As you go, you're going to see why. Okay. What we're going to discuss today are some power derivatives, some power shortcuts, we could call them. And, some of these you might already know if you've been paying attention. But just to see them like laid out as sort of a little proof with the formula is sort of fun. And what you're going to find as we continue to move through this chapter is we can do this process that we're going to begin today with all kinds of functions, trig functions, exponential functions, and then we'll use that to discuss logarithmic functions and inverse trig functions. So I don't know. I think it's exciting. Let's go. All right. In this presentation, we are down to here. Okay, this would be the last page of the printable notes if you have those notes. If you don't, no big deal. All right, the first thing that I want to talk to you about is this notation. So all it says here is find d over dx parentheses x squared. What you need to know right off the bat here, let's do blue, is that this d over dx means find a derivative. Okay. What looks really different today is that you are not given a specific point, a specific x value to find your derivative at. So I'm going to show you how to set up your ordered pairs so that you can use the formula to find your derivative. And for this first one, just so you know, I am going to go back to the original definition, which I'm just going to write up here so that we have it to refer to. You can say that f prime, we're just going to call this f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, but remember that's coming from the slope between 2 points that we define. So let's go over here and I'm going to show you right now how to define those 2 points. Because we are not given a specific x coordinate this time, I am going to just use an x to define my first x coordinate of my first ordered pair. Okay, and that means that we're using the function y equals x squared. So the y coordinate would come from x squared. Again, if you want to label that x1, y1 as we've done in the past, because now it looks similar to what we've been doing, right? Go ahead and do that. The second ordered pair, remember we're back to using the original definition, and that means we can define the x coordinate for the second ordered pair as our first x coordinate with h added on. So x plus h. Comma, put that into your function to get the y coordinate, and that would be x plus h quantity squared. Do not write that as x squared plus h squared. That's going to need FOILed. We can identify this as x2, y2, though, if you think that would be helpful. So now we are finding a derivative, and this time again, since we are not looking at a particular x coordinate, we can just write that as f prime of x. Okay. It starts with a limit as h approaches 0. And then remember, you are just doing the slope formula, y2 minus y1 divided by x2 minus x1. And so in that case, that would be x plus h quantity squared minus x squared. All over, it would be x plus h minus x, but remember that always just simplifies to h. So let's just put an h down there. Now, our goal is still, as usual, evaluate the limit. Sub 0 in for h. You cannot do that right here because you will get 0 over 0. But let's write that limit to keep in mind that that's what we're doing. And let's expand the x plus h squared, the quantity x plus h squared. That's x plus h times itself. We've talked about that a lot. So, I don't really need parentheses there. I hope we're comfortable with this. X plus h quantity squared would be x squared plus 2xh plus h squared. If you need to do this off to the side to confirm that, do this, then go ahead and do that. But that's what you should get out of that. Bring along the minus x squared and the all divided by h. Okay, can you see it? I don't know. At this point, usually my students have done so many, and I've actually already told you what the answer to this one is. 2x, right? Can you see it right there? I'm excited. Let's do it. Okay, x squared minus x squared cancels. F prime of x will come from the limit as h approaches 0 of what remains in the numerator has a factor of h that can be taken out. So h times 2x plus h, all divided by h. Cancel here, here. We now have the limit as h approaches 0 of 2x plus h. Sub that 0 in. So f prime of x equals 2x. For f of x equal to x squared. F prime of x equals 2x. Woo! We proved it. Okay, so I'm so excited about this because here's why. We now know that if we have the function x squared, then to find the slope along that curve at any point, we just take that x coordinate times 2. Okay, and that means we are done using a formula like this, a limit formula, to find the derivative of y equals x squared, to find a derivative value. Okay, here's the function. Here's the shortcut. That's what we're looking at. All right, and we're going to do a couple more now that we can use, and then, very soon we will start to discuss rules and properties of derivatives and all sorts of good stuff that's going to move us away from this limit as h approaches 0 or limit as x approaches a definitions and, take us to a much easier place to find our derivatives. Okay, so very exciting stuff. Okay, this is a you try, and if I was actually in class with you, I would say have at it. You try it, you should be able to do it, no problems here. If you want to pause the video and do that and then come back to me and see if we end up in the same place, I encourage that. But I am going to go over it just so that you can see it here. I'm going to use the, I'm thinking. I'm going to use the original definition, I guess. However, you could use the alternate. You would have to, if you're going to use the alternate definition, you would need to know how to factor a difference of cubes, which isn't too bad. But I'm going to go ahead and use the original. So original definition, let's identify the first ordered pair as x comma x cubed. Again, no specific point here. Oh, by the way, differentiate, that's a verb we use in calculus that means take the derivative. Okay. Differentiate y equals x cubed with no given ordered pair to start, no given x coordinate to start. Let's just identify our first ordered pair as x comma x cubed. Second ordered pair, because we're using the original definition, is x plus h comma, quantity x plus h cubed. x1, y1, x2, y2. Y prime, I'm going to write it as y prime just because this is identified as y up here, is the limit as h approaches 0 of the slope y2 minus y1 over x2 minus x1 would go to h. Now, x plus h quantity cubed, you know, that might be some side work that you need to do up here. It's x plus h times x plus h times x plus h. Okay, when you FOIL here, we just did that. We got x squared plus 2xh plus h squared. Put parentheses around that, bring down the additional x plus h, and now you're just distributing the x to each of these pieces. And then you're distributing the h to each of these pieces. It looks a little bit yucky, huh? I'm going to put, when I distribute the h, I'm going to put that stuff down here. I like to line it up like this. Watch, h times x squared. I can write that as x squared h. And do you see how I lined it up with this term because they're like terms? H times 2xh is 2xh squared. See how I lined it up with this one? And then h times h squared is h cubed. All right, this is just like side work because I needed to expand x plus h quantity cubed. I'm going to put the next step of my derivative down here. So x plus h quantity cubed, it becomes x cubed plus, let's combine these, 2x squared h plus 1x squared h, that's 3x squared h. Combine these, xh squared plus 2xh squared is 3xh squared. And then we have an h cubed. That is x plus h quantity cubed expanded. Now bring along the minus x cubed and all divided by h. Add to 0 here. Yay. I say yay a lot. You're just going to have to get used to it if you want to stick with me here. I'm not, it's just something that pops into my mind, so I say it. Do you see what I'm doing now? After I canceled the x cubed terms because they add to 0, I am factoring an h out of what's left in the numerator, as we've done so many times, to divide with the h in the denominator. And we now can sub-zero in. We have the limit as h approaches 0 of 3x squared plus 3xh plus h squared, which will be 3x squared plus 3x times 0 plus 0 squared, which is 3x squared. Y prime equals 3x squared. Woo! There's another one for you. So what we have here is x cubed. When you take its derivative function is 3x squared. Isn't that exciting? So you now know 2. All right. For this one, this last example today, we are going to look at y equals root x, and it just says find y prime, which is a nice, easy, that means take a derivative. Notice the directions all looked a little bit different for each one of the problems on here, but I just was trying to show you different ways that you could see like directions that mean find a derivative, okay? For this one, I'd like to show you the alternate definition, because I don't know if you remember me saying this before, but I do prefer the alternate definition when I am working with a square root function. Also, I just want to show you what it would look like set up when you don't have a specific x coordinate, because you have that a in there, and students say, well, how do I use the alternate if I don't have an a equals value? Okay, well, here's how you do it, everybody. You just define the first x coordinate as a, comma, root a would be the y coordinate in that case. The second x coordinate is just x, comma, root x would be the y coordinate. Here's your x1, y1, x2, y2. Let's go with our slope formula, but don't forget the limit. The limit as x approaches a. You're not approaching a specific value, you're just approaching the letter a of y2 minus y1 over x2 minus x1. Okay, so that's how we set that up. Now, I just need you to know that what we are going to get out of this is an expression in terms of a. You can then go back to saying, well, a is just an x coordinate. So we will then change that back into an expression in terms of x so that you can see it and how it looks like the other two that we did today. Okay, I'll explain that again when we get there. Let's just go with, what are we supposed to do here? We are supposed to multiply by the conjugate of the numerator. So I'm going to multiply by root x plus a over itself. Whoops, root x plus root a. Sorry. Put the numerator and denominator of your original expression in parentheses, and let's go down here. Let's expand, like multiply through in the numerator. So root x times root x is x. Root x times root a is root x, root a, or root xa, but it doesn't matter. I'm not going to write it because I would have the negative version of that when I do my inners, and they would cancel. Root a times root a is, negative root a times root a is just minus a, or negative a. Okay, are you good with that? If you need to, like, again, do a side calculation, whoops, or a little side work step like this, and then like work out what I just talked about, do that. Okay, I'm just sort of glossing over that because we've talked about it numerous times in class. So, I just want to keep this video kind of short. I am not going to distribute these through in the denominator because I see this x minus a will cancel with that x minus a, and I want that to happen. So now I have the limit as x approaches a of 1 over root x plus root a. And at this point, I can sub a in because I canceled that x minus a. So what I'm left with is 1 over root a plus root a. And that is 1 over 2 root a. All right, now this is what I was talking about with taking the a and turning it back into an x. I'm going to write a statement down here. I'm going to say for y equals root x, y prime is equal to 1 over 2 root x. You can change that a back to an x if you would like to do that. You actually, this is kind of crazy, but you could actually write this as the limit as a approaches x and turn your points around, and then that would do that as well. It's kind of weird and students don't like that. So usually I just say, let's go to a like we're used to doing, and then we'll go back to an x form. Or there's one other thing I want to highlight here, and it's going to be important when we start to talk about something in section 3.2 and 3.3, and that is that this could be written as a power. Like all of this statement could be written as an x to a power, and that is going to be really helpful. I promise you. So I'm going to write for y equals x to the 1/2. Because for y equals x, the square root of x, that is the same as x to the 1/2. Then y prime is equal to, and I'm going to write this expression as x to a power. I have this 1/2 here, Let's put an x beside it, and it is a square root of x again, so it's a 1/2 power again. However, since it's in the denominator and I'm taking it out of the denominator, I'm going to write it as a negative 1/2 power. Okay, and that might look a little bit messier or yuckier than what we have over here, but I promise you that this is actually what you're going to remember for the most part when we discuss, oh, why did I do that? When we discuss the derivative of the square root of x from now on, okay? And so if you haven't figured out like this overarching power rule, okay, that's what we're like sort of getting at here. That's what we're driving toward. You might want to just write these statements like in a little notebook and sort of look at what's happening. Try to see the pattern here. For when we have x squared, the derivative becomes 2x, and I'll tell you one more thing. It's like a 2x to the first power. That's helpful. Okay, here, where am I going? Here, when you have x cubed, the derivative is 3x to the second power. And finally here, when you have x to the 1/2, the derivative is 1/2 x to the negative 1/2 power. So again, what I encourage you to do is look at those examples and come up with what is called the power rule for derivatives. It's so, oh, listen to this. I can remember I don't know if it was last year or the year before I came up with this. I said, the power rule is so powerful that it's pretty important that we figure it out pretty soon here, okay? All right, that's it for this video lesson. We uncovered some pretty important things today. As usual, I hope this was helpful. Bye.